this presentation is going to be about energy efficient fan technology for HVAC retrofits, new construction.
Yep.
Is that generic enough? And presenting today we have George Niksic. CET. Make sure you get onto YouTube. You might as well come up and stand with me.
No. I forgot you were recording.
George is with Aqua Air Systems, and that was his partner, Kibitzing in the back. So.
David Lima.
So anyway, George is a certified engineering technologist, CET, having graduated from State HVAC design program. It's been a while since that's been up and running. Eh?
Yeah, that was 1991, I think. 90 or 91, I graduated, yeah.
George has 20 years experience in management roles throughout several industries, 14 years in HVAC, testing, design, and sales. His current role is business development with Aqua Air Systems, works with David Lima, and is currently serving on the board of Southern Alberta chapter of ASHRAE as RP chair, which I don't remember what RP chair is. So
it's for the RP chair.
Yeah,
yeah, it's for research and development.
Well, there you
raising
go.
funds for that.
I knew that. Anyway,
thank you.
There you go, George.
Hold your applause.
Yay! Very good. Very good.
Get the guy go! All right.
Thanks, Mark. And first of all, I'd like to thank BOA for having us here today, and the big crowd that showed up today too. Thank you. Today we're going to talk about fan types, application, and retrofits. Oops. This being a BOA event, I thought this slide might be relevant. How many here have probably seen a slide or a fan that looks like this or in the same condition? In HVAC and most mechanical equipment, the lifespan of the equipment is about 25 to 30 years max. Believe it or not, there's a lot of buildings downtown Calgary and all over Calgary that still have equipment that may be well beyond their lifespan. When we talk about fans in HVAC, the two main types of fans are centrifugal and axial. In the centrifugal, you have forward curved blade fans, backward inclined flat blade, backward inclined airfoil blade. And if you look at the pictures, this is your standard housing for, that would be a forward curved DWDI fan. You'd have this mounted on a base with a motor and pulley to drive it. This is a plenum fan. You'd also probably be mounted on an isolation base, the motor and pulley driving it. Axial fans, you have the tube axial and the vane axial. When we talk about forward curve fans, probably the most used fan in the HVAC industry over the decades. It's been your standard forward curve fan. Looks like this, like we said, with your standard housing here. The blades are curved forward in the direction of rotation of air, and it kind of scoops air with that forward curved blade. Less efficient than an airfoil and backward inclined fan. Requires the lowest speed of any centrifugal fan to move a given amount of air. Used for low pressure HVAC systems. And like I said earlier, these will be mounted on a base with a pulley and drive system. They're not the most efficient fans. We'll talk about fan curves. But whenever you have a motor and a belt drive system, there's additional losses to the overall system with that. Backward inclined flat blade was one of the first inventions or engineering improvements for efficiency on blades. Backward inclined blades and single thickness, or they're single thickness and flat. They curve away from the airfoil as it rotates in the direction of airflow. Efficiency is only slightly less than the airfoil blade fan. Airfoil blade fan, the slight difference, which we'll talk about in the next slide, it's got a rounded edge. This is just the flat blade. These push on the air, often used in the pressure fan applications. These fans are backward inclined and a airflow blade, you get efficiencies in the 80 to 85 range, which I forgot to mention on the forward curve. You're probably looking at a max of 60% efficiency. The backward incline and the airfoil blades, same HVAC applications. They're most often found in moving primary air within an air handling unit. They're also for industrial applications where airfoil blades is not acceptable because of corrosion or erosive environments. With the airfoil blade, it's curved at the front. For the roads, you'd have a hole in the blade, so the backward incline is used in those cases. Backward inclined airfoil, as the name implies, the airfoil like an airplane wing shape on the front of the blade. Also like the backward incline, it inclines away from the airflow, kind of pushes on the air rather than scoops air like a forward curved blade fan. The airfoil on the end of on the leading edge of the fan blade makes it more efficient, slightly more efficient, because as it cuts through the air on the other side and coming over the top, the airfoil blade just cuts through that air a little bit more efficient than a flat blade does. So these are developed to provide high efficiency, like we said, in 80–85% range is possible, used on large HVAC and clean air industrial systems where energy savings are prime importance. If you look here, when you look at a backwards inclined fan and a forward curve fan, they often came in that traditional housing. The backwards inclined airfoil fan, you can see this plenum fan arrangement that became very popular. It's a pressurization fan. We'll talk about some of the advantages there, but it was another improvement in the efficiency of how we move air. So when you talk about forward curve blade fans, this is a fan curve. I don't know how familiar people are with a fan curve, but it measures static pressure, CFM, and horsepower. The main driving factor on a fan is the static pressure. And with forward curve fans, you see here, we talked about curved forward in the direction and rotation of the air, large volume, low static pressure, slower speeds, small size for a given volume, lower to medium efficiency, must be properly applied to avoid unstable operations. This is very important, and when you're selecting a fan, this green line here, as you can see, curves up to the peak, down, and then back up again. You want to be no more than about 90% of your maximum static pressure on this side of the line of that curve. And also when you're calculating, another important thing when you're calculating your external static pressure, you want to make sure those things are right, because if this sneaks up on the side of the line, you get to the top, it could end up surging. If it gets down on this side, the fan will speed up, slow down, speed up, slow down sort of scenario, because they are overloading, they speed themselves up. In severe cases, if it's unchecked, your static pressure continues to rise, the fan will speed up, kind of like running down a hill. It just can't stop itself. It could fail, complete failure of the fan. So it's very important that you get this selection correct. Must be properly applied, just so that for the unstable operation, clean air and high temperature applications. You'll still see these forward curve fans sometimes in furnaces and all over the place. Backward inclined flat and airfoil blade. We're showing the one curve here because they're very similar. Like I said, the real only difference is the shape, the front edge of the blade, and the efficiencies are very similar. They're higher volume at moderate pressures, higher speeds, non-overloading power characteristics. How does that compare to that forward curve fan? If you look here at that green line, it goes up, gets to a peak, and curves down. So you also don't want to be at the top of the curve. You want to follow that same basic rule of 90% of your static pressure stay on the right-hand side. But if it happens to go over, it won't overspeed or speed itself up. It's almost a self-regulating. It won't go over the design of what it can do. It just won't push any more air or build any more static pressure. Low abrasion resistance, high efficiencies, again in that 80–85%. That's where the stable performance characteristics, that's why the fan was invented. It's much more efficient at moving air. Lower noise, and generally used for clean air use. When we talk about fans, we should also talk about the discharge profile and why it's important. If you look at this house fan, what we were talking about originally with the forward curve and sometimes backward incline curved blades, this is that base that I was talking about. It would be mounted on with isolation. You got your motor. We don't show the belts in here. That's where the drive losses would be added. But when you talk about the discharge profile, these lines here, upstream of the fan. This fan is spinning very, very fast. And one of the rules of thumb in HVAC whenever you're designing a system is 500 feet per minute. Everything else in your air handling unit, your coils, your filter banks, even the air handling tunnel itself or the air handling unit are designed to 500 feet per minute. When it gets to this fan, it's going to be throwing out the front discharge of this fan area here at 3,000, 3,500 or even higher feet per minute. And most of the volume will be at the top, and it tails off as it goes down towards the bottom of the fan. That's the fan profile. As you can see, these filters in front, if these are the final filters and you had most of your velocity and your air volume going to the top, what do you think is going to happen? Those top filters are going to load up a lot faster than the bottom filters. It's unrealistic to think that an operator is going to go and rotate his filters and ensure that they load correctly. You're going to change them all out, so you're wasting the square area or the design that you built in for the changeout, so it's going to cost you more money, which in turn affects your efficiencies. If you look on the downstream side of things, why is the profile important? Well, the fan is sucking DW, DI, dual inlet, dual width wheel, most common. It's going to be drawing off more of the center of the coil here and the side. So if you were to look at it like this, you might be getting what, 40, 50% of your coil. When you design a coil as an HVAC designer and engineer, you're designing the heat transfer at 100% of your coil area. If this fan, out of its nature, is drawing just off the center, you may be getting 50% of the coil area. So what does the system do? It has to get more air, you have more hot water, so your boilers and chillers are working a lot harder to meet the load because you're not utilizing the entire coil system. One thing in this design that is important to talk about, this distance here makes the footprint of these units a lot larger than the other fans that we'll talk about. And why is that? You have to keep this space to help the air be less turbulent or laminate flow. In some cases you can have, with this top filter, if this was too close to the outlet, you can damage that top filter, or it might even blow it out. This is a front loading face one, it looks like, but still, you're talking about really high velocities. You can correct that through air blenders and other things, but then your unit just gets larger and larger and larger. Typically with this, when you have a discharge like this, you'll have one opening in the bottom, opening in the roof, say, or opening in the end. Plenum fans, great improvement, works on pressurization. When you talk about the fan discharge profile of this fan, as you can see, the orientation of the fan is a bit different, still on the base with the spring isolation, belt driven, so you still got the belt drive losses. But as you can see here, this fan is spinning and it's pressurizing this area, so it's really a turbulent spinning blender type situation in there. So it pressurizes this section, and then really physics does the rest. Air wants to move from high pressure to low pressure. It's lower pressure on this side. It's going to travel through that filter. But because this is swirling air, but it's moving much more uniform through these final filters, so you're going to get better loading on your filters. You may not get a 100% even throughout, but definitely better than if you saw that other profile. If you look downstream here, you've got the coil. Again, you're going to utilize maybe 70% of your coil. Maybe it's hard to to calculate how much more effective it makes it, but you're going to be more effective because the profile as it comes off the coil, you're going to use more of that coil in that filter bank. One good thing about pressurization fans like this, you can have multiple. It's not shown here, but you could have 2 in the ground, 2 in the end, 1 in the roof. Any combination that you would need or could dream of, you can put more openings on in there. This tends to be a little bit, because you don't have that discharge distance that you have to watch, the footprint be a little bit smaller than if you're using the standard fan that we looked at in the past. Fan wall discharge profile. One word to best describe the profile on this is extremely uniform. Or I said one word, uniform. Bad one there. But why and how does it do that? You have similar like plenum fans here, but you have multiple smaller fans with smaller direct drive motors. Why is it important with the direct drive motors? You don't have belts, you don't have belt losses and drive losses. So that all also improves your efficiency. As you can see here, we're talking about the final filters. These arrows are indicating the profile of the air you're going to utilize, near 100% of the filters square area that you designed the unit for. And if you look at downstream, same thing, the profile is very even. This is like pushing a big wall of air through the air handle. And you don't have those high turbulent velocities that you would have one giant fan. So here you're going to maximize the effectiveness of your coil. By doing so, your boiler load and your cooling chiller load are going to be less, which would equal to more efficient operation of your system, and also would save you money in the long run with your energy costs. Like the plenum fan, we're only showing the one opening here, but again, you could have multiple openings on the other end of this unit if you require them. In general, the fan wall, because using smaller fans and motors, you're going to have even a smaller footprint of a unit than most design units. Talking about that, a good way to envision how that wall of air is moving towards you in a unified manner. Here you're looking at the upstream of a plenum fan. As you can see, that plenum fan's spinning very fast. It moves very fast in the center of the fan, obviously, and your volume's still pretty uniform. You've got the outer edges that aren't maybe moving at the same speed as the center. And here they're just showing it, I believe, you can't see there, it's 12 inches upstream. If you go over and you look at it and you compare the fan wall, and you can see this with the multiple fan wall fans in there, you've got a very uniform wall of air moving through the system, how the system was designed. Everything else in the system, so why not have the fans do that? You can see that again, 12 inches upstream. This is showing the plan view or the top view and the side view. As you can see with the plenum fan, the profile downstream looks pretty good. Not bad compared to that directional fan that we were looking at. But you can see all this turbulent air that this big fan, so say this could be 100 horsepower, 50, whatever the horsepower is, a big fan moving, turning a lot of air to pressurize that area. Looking at the fan wall, again, on the downstream side here, you've got a very even wall of air moving through. Still turbulence, but less turbulence, smaller fan, a much more uniform flow. Tube axial fans, as I mentioned in the beginning, your centrifugal fans most often are moving primary air or air within your air handling units. The tube axial fans, as you can see down here, more efficient than your standard prop fan. One of the reasons they're more efficient, this cylindrical housing fits very closely to the outside diameter of the blades. These are for low to medium pressure ducted HVAC systems, used in low pressure industrial and commercial applications. You can see here too, they've got a direct drive and a belt driven. Sometimes you can't have the motor in the airstream, so you go right with a direct drive. Direct drive also more efficient. Often you'll see these fans tucked up in a mechanic room up high in a round duct, moving maybe exhaust air or return air. Tube axial fans, much like the forward curve fans, they can overload, so again you have to be accurate on your selection. You want to make sure you stay on the right hand side of the curve. You get over the other side of the curve, the overspeeding, that running downhill can't stop the fan. They're not super efficient, but they're an effective way to move large volumes at low static pressure. Vane axial, the biggest difference, well, the really only difference for vane axial fans are these straightening vanes here are added. What do they do? Well, the straightening vanes allow for greater efficiency and pressure capabilities for medium to high pressure HVAC systems, and you can see it in there. The vanes just help it smooth the air and build up a little bit of pressure. Not much difference in the fan curve from the tube axial. Same thing, they have overloading characteristics. So again, you don't want to be on the right hand side of that. You can have an overload situation. Here, it looks like they're using them in the case of for an exhaust fan application. Aerodynamic stall causes the performance curve to dip to the left and peak pressure, which should be avoided. So that's what we're talking about with the fan curve. Another big invention that helped efficiencies in the HVAC world was VFDs. Before the development of VFDs, a lot of systems, there was a set point, the system would come full on, to meet set point, when it met set point, full off. And with VFDs, VFD stands for variable frequency drive. VFDs are based on the demand of the system, and they vary your capacity, or they vary your system to meet the capacity within this that is calling for. And how does it work? You have a building management system here that sends out a 0 to 10 volt signal to the VFD. The VFD is programmed to interpret that signal. You can decide what that means, but in this case, it's interpreting the 5 volt signal to be 1750 RPM. So what it does, it interprets that, sends out, if this was a 60 hertz motor, it sends out 30 hertz to that motor. The motor's going to run at about half speed. You get half your capacity in the system, so you're adjusting your system or varying your system to meet the demand, which is more efficient. If you keep tighter control of your system, it tends to be more efficient, and it only meets the demand. It doesn't come full on and full off. It's varying everything, including VFDs are often used on other parts of the system, pumps and all that, so everything's slowing down just to meet demand. As you can see in this situation, you have one VFD that's controlling one fan. When we talk about fan walls and VFDs, we have a little bit different of a scenario. There's more options for controlling the fans because you have more fans. You can have a single VFD controlling, say let's say we had 10 fans in a fan wall application. You can have one single VFD controlling all 10 fans. There'll be smaller motors and all that, but it'll adjust all 10 fans to meet the load. You can have multiple VFDs. So if you had 10 fans, you could have 2 VFDs, each running 5 VFDs, each running 2, whatever scenario you think would work. We're going to talk a little bit about redundancy, but we'll talk about redundancy in fan walls in general. The good thing with fan walls is if you have 10 fans and one fails, you still have 9 fans and motors that are operational. Your VFD will adjust the other fans that are operational to try and meet demand. And in most cases, when you're designing an HVAC system, you're designing for your winter and summer extremes, but that's not where your system most of the time is running. It's running somewhere in between that. So in most cases, if you had one fan fail in a fan wall application, the other ones will speed up. You wouldn't even notice it probably meets set point. If you're on the extremes of a minus 30 day or a plus 30 day, you're still going to have air moving, even though you may not be at the full capacity. You might be at 90 or 95%. You still got air moving, you still have cooling and heating available. The BMS will let the operator know that there has been an issue with a motor. You might have a light come on in your panel, but it's not a big panic to go and replace that motor right there and then. Contrast that to a single VFD with a giant motor, say 100 horsepower, 125 horsepower motor. If that fan goes down or that motor goes down, now it could be an emergency situation if it's at the extremes. If it's minus 30, it doesn't take long for the pipes to burst or freeze and burst. And if you have a more critical environment, say you're a hospital or an old age home, it could be a life safety issue too. It doesn't take long for minus 30 to freeze everything. And you can imagine if you have to go find yourself a 125 horsepower motor and install it in an emergency situation where you have no airflow, installing or removing a 5 or 7 horsepower or a 10 horsepower motor and replacing it is a lot easier. And you can do it again at your convenience. You don't necessarily have to replace it immediately. Of course, everything breaks on a Saturday or Sunday night. When we talk about full redundancy, if you have a really critical environment that you're controlling, and you do not want 9/10 of performance. At the worst case scenarios, you need 100% capacity, like in an operating room, hospitals, maybe you have a controlled condition manufacturing that you have to maintain that temperature and airflow exactly. You can build in everything from redundant drives. A redundant drive, if one drive fails, which is very rare, drives don't fail that often. They have a very long lifespan. If it does fail, it will switch over to the other drive. Again, your building management system would be alerted that was an issue, but your system will run at 100% capacity on that drive. If you need the 100% capacity through the entire system, what we do is you can do N1, N2, which is if it's N1, you want one extra motor and a fan, and you build it into the fans themselves and the motors. You'll have extra capacity by adding a couple extra fans or an extra fan and motor. And when one fails, a light will come on in the system letting people know that one's failed, but the VFD or multiple VFDs will speed up the rest of the fans and you will get 100% capacity. The system runs just as it would if that fan hadn't failed. And again, then you can replace that at your convenience or schedule that replacement. Some people will buy an extra fan, housing, and motor to keep in stock just in case that happens. Another way to have redundancy. Fan wall technology, how has it helped with retrofits? Well, if you've all been in buildings, the mechanic rooms and the HVAC equipment is often buried deep down in the basements, high up in the upper floors, or even if it's on the main floor, like in schools we've been in older schools, it's on the main floor, but they built the building around the HVAC or the mechanical room. So with that said, even if it is on the main floor, 25, 30 years ago plus, they weren't thinking much about how do I replace this equipment or how would I improve the current system that I have. So adding some building, checking them. These really are maintenance free. There's nothing to do with them. You can check your building management system in the morning. If they say everything's running fine, everything's running fine. You don't have to go walk in, open them, have a visual inspection, check the belt tightness, all that stuff that you'd normally have to go through with the old style fans and belt driven.
Wow.
Well, thank you. That's about it for the presentation. I know you all waiting and dying to ask questions.
I have a very excellent question, I think.
Well, we'll be the judge of that, Mark.
Well, seeing how all the energy guys have all left the room.
Yeah.
So let's do a little bit of shaming here.
I love that.
So one of the most, this has always been a challenge,
Yeah.
in my HVAC experience, lifetime, whatever. But condenser units.
Okay.
And now with different refrigerants, and we're trying to optimize the refrigeration process to try to control. Well, we run the condenser fans, some on pressure, some on temperature, various scenarios, but we never really had the finite fan control that we really needed for the process. Why did that matter? How much energy are you burning thrashing compressors when you don't need to? So this type of technology works well in that application. And I see some new stuff out there that's got an adaptation of it, but it's not really a very good attempt by some manufacturers that will remain nameless. However, from a building optimization point, that's low-hanging fruit to me. And so we'll have to talk about this some more. But I mean, it's.
I have an answer for that one, but there is equipment out there.
Yes,
like
there is.
Chillers now. And what they do now, like we have a chiller, it's basically like a fan wall, and you can run it year round, so it has multiple compressors, and you can design an N+1. But when it gets cold, it uses a pump, shuts off the compressor, pumps the refrigerant outside, so it cools off and pumps it back in.
Oh.
So you get free cooling on an air cooled. And what we do also is each fan on the condenser has an ECM motor, and you can kick them in 2 at a time. So you don't have to use all 10 or 12 or whatever, just popping them off and on. And there'll be variable speed too. So today you actually have a lot of fine.
So
Yeah, you can have a variable speed, one variable speed compressor and one on-off, so it comes on and the variable speed makes it maintain, instead of having it just slam on and off. Like we were
But
talking.
typically all the VFDs, like in our chiller starts off at like 2 amps. Like it's, and then they vary right up, but we're talking like mag bearing, oil-free chillers, and I mean, a flat screen TV makes more noise than mag bearing chiller.
Yeah, the mag bearing, there's no resistance, all magnetically floating in the
well,
bearing.
No oil.
and you're right that the acoustic problem is a big one. Absolutely.
Vibration, and that's, on a smart chiller, you don't even have spring isolation on it. It sits on the concrete, and you don't know it's running.
But anyway, from a retrofit perspective, or optimizing the existing equipment without having to sell the farm here, I mean, it's not that expensive to do some retrofit.
Everything you get what you pay for in life. You know, you pay now or you pay later. That's the secret. Nothing changes.
But
You are right with the variable, everything should be variable. It's amazing how much
well,
energy
you
you're
can
saving.
control the refrigerant process. You can optimize the process to try to get the most you can out of what you got.
Everything has a VFD today. I call them just a smart dimmer switch, but it just makes it easier to control your inline rush. And you control with a pump. A pump is very efficient because you got full flow all the time. On an HVAC, it's not as efficient because you got almost 2.5 inches of variable in your filters as they're loading up. So you need that VFD to go up and down. As the filters load up, you need to increase it so it's maintaining a set point of a certain CFM or duct static, whatever it's designed to.
So Dave has a good story that he was telling upstairs too about when he installed the fan wall, he thought it wasn't working. So it was running so slow, hey Dave? And because it was meeting demand, so which means you got less load on your chiller and your boiler and all that. It wasn't running simply because it didn't need to necessarily run at that higher volume. So Dave had to go there and he's like, whoa, what's going on? How do I figure this out? And
It took me a while.
and he's like, okay, it's running very quiet. Everybody's thinking, this thing's not working. Dave's thinking, geez, what's going on? Turned up the static pressure. And he said, hey, bring on more static pressure. The unit said, whoop, hey, we need to meet demand. Thing fires up, full load. He's going, see, it's working. But that on-off and meeting a set point, shutting on and off, like I said, variable and maintaining. So the system was just running enough to keep, satisfy the load. So it was running very slowly or very, not at max capacity, and it was satisfying all the loads. So you're using less energy. So.
Well, yeah, anytime you can control your static pressure easier, and
Well, this system was an odd system because it was at the Calgary Airport, and it was an old hot deck, cold deck. And because we changed the fan system to a fan wall, now all of a sudden we're using every square inch of that coil. So you got a piston out there. And what was happening was the old fan, like George mentioned, you got that high velocity in the coil, so you're only using maybe 40, 50, 60% of it. Put in that fan wall, was using 100%, satisfy the boxes, they closed off. So we didn't need all that static. So the airport's like, I bought a 45,000 fan, but it's only delivering 18. What's wrong? Well, I don't know. Everything, you guys comfortable? Yeah, everything's good. And it took a while to figure it out until I asked Johnson Controls to open up all the boxes, and then boom, it just blew wide open to 45,000 CFM. And then they just went nuts and refitted the whole airport, and the old one and the new one is all fan wall.
got anything to throw in there, Dan?
I have a question for the presenter, George.
I'll let you go.
Sure.
Thank you very much.
Thank you. Good
Yeah,
to see you again.
that was fantastic. Thank you very much.
Thank you very much.
We'll touch again.
Yeah.
So, George, is there some kind of cost correlation between, I'm going to give you an example. I take a 5,000 CFM air handler and I put in a fan wall. That's an extreme, just so you know. Or I go to 100,000 CFM with a fan wall. So what I'm saying is there like a cutoff where just use the conventional fan because of the CFM versus going to a fan wall for cost?
You could, it'll go down to the lowest CFM, but anything in economy is of scale in general. Your cost per CFM on higher volumes is going to be less than when you get down to the lower CFMs. A lot of that has to do with, you know, cost of VFDs and controls. And just in general, just like when you sell a smaller air handling unit that's of a better quality, it's going to be a little bit more money than when you're moving 50,000 or 30,000 CFM. So there are some economy scales, but it's not, you could do a 5,000 CFM fan wall.
Well, you could.
Yeah, it's.
It would be, might be just one cube though.
Yeah, it might be one cube. You could go to 2. You're seeing a lot more.
It scales out of
Yeah.
economy.
No
Fan wall
maintenance.
is typically more expensive.
Belts have to be
bigger the
replaced.
unit, and then you actually get a lot of savings on size, the footprint.
Yeah.
And that's how basically an air handling unit, the bigger the footprint, the more cost it is. But then you gotta look at it, the owner's point of view. A mechanical system is an overhead, and a mechanical room is, so if you can make a smaller mechanical room like in a hospital or in a school, you get more bums or beds in, which is your money making. Some of the mechanical rooms we have at the universities, I mean, they're like 30, 40 feet high, and they're a whole floor. That could have been, you know,
More space.
two office floors of, you know, children learning, making money. So smaller footprint does matter to the owner.
How